So I'm going to basically give a pedagogical talk today on an aspect of my master's thesis, which was on primordial black holes. But of course, I'm not going to discuss my thesis today because it would take a long time. So what I will do is basically try to probe the intrigue that people have, particularly in early universe cosmology and also black holes. So of course, we understand that black holes in itself is a mysterious thing. And most of the time, people are always asking questions of, how did black holes form, or, what are black holes, where do they come from, etc. And also, alongside that, people have questions about the early universe. How did the universe begin? How did the universe come from? Where did it come from? And what were the exact physical conditions that led to the universe that we see today, right? So today, what I'm going to do is basically try to bridge both of these topics and try to probe the questions to how black holes are formed in the early universe. Okay, so first of all, I'm going to start with like a little bit of historical context. So maybe it's better if I can speak in both languages. It'll be convenient for me. তো আমি যেটা চেষ্টা করব বলার সেটা হচ্ছে যে historically why did we think that black holes were forming in the early universe? Because আমরা যেভাবে বুঝি যে early universe conditions were very very chaotic. Right? And black holes are something that are, at least from our understanding, should form when stellar objects collapse, right? Or stellar objects die. So in that context, we don't have stellar objects in the early universe. So why did people come up with the thought that, there could be black holes that existed in the very early universe? In fact, it comes out from this concept, which is called Meissner's chaotic cosmology, where basically there was a physicist called Charles Meissner, and he postulated that the universe was actually turbulent and oscillatory when it was first beginning. Okay, what that means is when we see the universe today, we see it to be homogeneous and isotropic, right? What that means is it is translationally and rotationally invariant. Basically, when you stand wherever you are in the universe, wherever you look, if it's rotational or translational, the universe looks the same to us. However, that was not the case in the very early universe. In the early universe, the universe was definitely chaotic and oscillatory and went through a turbulent phase. I thought, study this particular universe. In general, when we use anything to study the universe, what we do is we sort of solve the Einstein's equation. So he did that. Particular solution of the Einstein's equation, and he started studying that. And that particular Einstein's equation solution was called the mixed master universe. Okay, and the reason why this was a probable solution was because it has similar characteristics to the FLRW universe that we see today, model of the universe that we predict. So therefore, what he did was he tried to bridge between the two and use that particular solution, which is the mixed master, to study the early universe. Okay, so the mixed master universe is important. It shares the same topology. In fact, particularly a closed FLRW, which can be topologically modeled as an S3, three-dimensional sphere. And mixed master also has this particular topology, except where the FLRW is dynamically characterized by only one factor, which is the scale factor. But the mixed master universe has particularly three. So it is dynamically determined by the scale factor, which is given as A of t, and beta minus and beta plus. Okay, so these are basically shape parameters that sort of introduces deformations in the space. Okay, so what this does, basically what these parameters do is it tends to maintain the homogeneity of the metric, but it breaks isotropy. So that means you have deformations, which means rotationally now if you're looking at the universe, it does not look the same anymore, but translationally it's still the same. Okay, so it maintains one type of symmetry, but it breaks the other. Okay, so physically or intuitively speaking, what that does is it gives you a solution where you have different deformations in different points of space. Okay, so think about this. If I have an FLRW And of course, indeed, it's homogeneous and isotropic, means it's translationally and rotationally invariant. So wherever I stand in the universe, I would look at the universe to be coherent everywhere, right? But let's consider mixed master, where I have now two extra shape parameters that define this particular universe. If I'm standing wherever I have, depending on the shape parameters and how they evolve, I would see different patches of space. Does that make sense? Because you understand that these shape parameters are giving rise to deformations. So some point in space can be deformed more than the other point in space, depending on what these parameters are in that particular space-time, right? So that means that in a mixed master universe, you can have places of very compressed space, and you can have places where there is, expansion, right? So that gives you a certain turbulent universe, essentially. So particularly looking at that space where you have compression, it might lead to overdensities. And what overdensities mean is that you have clump of matter or clump of substance in one area, and that clump of substance would naturally gravitationally collapse, right? Because of course the overlying interaction that these space matter would have would be gravity, and therefore if they are clumped up together, it is a natural extension to think that they would gravitationally collapse, right? So this was the idea, and he thought that of course if I have a turbulent space like this, there could be patches in space that could gravitationally collapse and particularly form gravitationally collapsed and compact objects. Okay, so this was the first idea of a compact object that could exist in the early universe. Of course, he did not coin the word primordial black holes. In fact, primordial black holes was coined by Hawking himself in his 1971 paper, where he worked with this particular solution of the Einstein's equation, the mixed master universe, and he predicted that we would have certain volumes of, so let's call them co-moving volumes, that would exist throughout the universe. So these co-moving volumes would essentially lead to the compact region that would eventually collapse to black holes. Okay. So of course he said that these volumes, since the shape parameters are different, so think about this, যে আমার particular parameter আছে beta minus beta plus, right? So depending on what these parameters are, I would have some of them to have, kinetic energy larger than its potential energy, right? And some to have potential energy larger than the kinetic energy, depending on what those parameters are. So if in case that you have your, let's say, gravitational force to be greater than the pressure in the region, you would have the compact object to gravitationally collapse, right? It's that's how stars basically maintain the internal pressure and gravity, right? So in case these compact objects are there, if the gravitational pressure is larger, depending on what the volume is that I'm talking about and what Hawking talked about, these compact regions would then gravitationally collapse, right? So what Hawking did was he sort of specified these particular volumes and said that these volumes would then produce black holes. Okay. Primordial black holes. And we call them primordial black holes because, of course, they are black holes that exist in the primordial soup, which is the early universe. Okay. Okay. So now a couple of questions. So আমরা বুঝতেছি যে okay, the possibility of these black holes existing in the early universe is probable. So there exists a particular theory that predicts যে okay, আমাদের primordial black holes exist করতে পারে. The next question to ask is how do they form? Where do they come from? We understand okay, একটা geometrical notion আছে. We have a certain, geometrical possibility that you can have these densely populated areas in space, etc., etc. But what is the actual physical process that gives rise to these black holes? Because we understand that আমাদের normal যে black holes বা astrophysical black holes এর কথা যখন চিন্তা করি, those astrophysical black holes come out to be from the death of a star, right? Where you have the Oppenheimer-Snyder process, you have the star to die, and then it gravitationally collapses to form a black hole, right? That is what we understand. However, if you think about the universe at that time, in the very early universe, you did not have matter, right? Matter did not form. And what I'm talking about is very early. In fact, this is like almost before baryogenesis, right? And baryogenesis is when you had matter to form. So if I'm talking about before baryogenesis, that means you did not have baryons, you did not have matter, the typical matter that we think about. So what actually formulated these black holes? That's one question, right? So what created these black holes? So now we know that these black holes were generated in the early universe. These black holes are not made up of typical matter, right? And these black holes are formed from overdensities. These are the three things that we know for now. Now, of course, if I know that they've been created in the early universe, I have to talk about an early universe mechanism that might give rise to these conditions, right? So, of course, the typical way to go is considering inflation, because that is the most viable theory of the early universe that we have today, right? So that's why what I'm going to do next is essentially recap a little bit of single field inflation, which will be hefty for us to understand how inflationary mechanisms give rise to the creation of primordial black holes. So I'm just going to breeze over this. So for people who may have not seen this before, but you're not familiar with how cosmological calculations work, I have a note over here that I prepared particularly for this talk, so I'll share it on the page so you can see it later on. So what we do normally is when we have, let's say, any space-time in GR, right? What we do is we want to formulate an equation of motion, because essentially in physics, and if you are doing physics for a long time, you should know that everything is governed by an equation of motion, right? So the go-to thing, if you want to look at something and analyze it, is try to see it from an equation of motion perspective. Okay. So of course, if you want to derive an equation of motion, you have to consider an action. You have to vary that action and then solve it. Equate it to 0 and then solve it, right? So the action that I'm talking about over here is going to be of the inflaton, because I'm talking about inflation, right? And inflation is probed by the inflaton potential, which is a scalar field. So I will have a scalar field action, which is given as follows, which just utilizes the Lagrangian of a scalar field. And I'm talking about single field. So this is one single scalar field that is probing this particular action. And my action will look as follows. Okay. So the next thing to do is vary this. Of course, remember that this is just the matter part of the action. I also have the gravitational part, which is given by the Einstein-Hilbert action. Okay. So varying the matter part, which is for this particular action, is the scalar field action. For this, I would get T mu nu, which is the energy momentum tensor, and let me denote it with phi to tell you that this is the energy momentum tensor for the scalar field. Okay. And this would look like the following. So of course, you're going to vary it with G mu nu with some normalization factors over here, and you would get T mu nu, which would look like the following. Okay. So now, using T mu nu, you can figure out the energy density, the pressure, etc. For people who have done cosmology before, you know this is a very natural step to go from the energy momentum tensor. So I'm not going to write it down or basically talk about the derivation as much, but I'm going to just denote what I would get as the energy density for the scalar field, which is going to be the zeroth component of the energy momentum tensor, and pressure, which is going to be the spatial components of the energy momentum tensor. And And from here, I can actually postulate the fact, of course, after some derivations, that I would get a Klein-Gordon equation-like equation for my scalar field that will look like the following. Okay? So this is my equation of motion for a scalar field that I'm probing the inflationary epoch with. Okay? Now, from here, you will understand a couple of things. That is, during inflation, you have the energy condition, which is called the strong energy condition, to be violated. Now, if you're not familiar with this, you can think of it as well, you can think of that era to have negative pressure. Okay, so normally when we have matter universe, as in let's say when we have radiation or matter or something that we know that exists in the universe, right? You have them to be defined by positive pressure. But during inflation, you did not have these objects probing the universe, right? There was something else that was actually more dominant in the universe, which was exactly this inflaton field. So inflaton field has negative pressure, and this can be shown via many derivations, but for now you can take it as granted that negative pressure was one of the dominating things in the universe that time. And due to negative pressure, your strong energy condition, which is given by the equation of state from here, is broken, and therefore it is also negative. Okay? And if we particularly probe this into our equations, we will see that this actually tells me that V phi, which is the potential of the scalar field, is greater than phi dot squared. What does that mean? That means essentially that you have a phi dot term, which is a velocity, right? Phi dot is a first derivative with respect to time. So that is a velocity squared, and a velocity squared term always gives rise to a kinetic term, right? So that kinetic term is less than the potential term, which must mean that whatever this motion is of the scalar field is moving really slowly, right? Because kinetic term jodi choto hoy, tar mane ki, mane it does not gain up much speed. So therefore it must be rolling very slowly in comparison to the potential, right? And hence we call this slow roll inflation. And slow roll inflation is indeed what gives rise to the ingredients that we need for primordial black hole formation. Okay, so now another thing that I want to discuss later on, now, is cosmological perturbations. And you will see that this is also something that gives rise to primordial black hole formation. Particularly in the inflationary epoch. Okay, so now what we have is inflation, and we have an inflaton field, which is the scalar field that is governing this inflationary epoch. Of course, when we think about any space-time, আমরা যখন normally কাজ করি এটা নিয়ে at its zeroth order, মানে হচ্ছে without any sort of disturbances or whatever, we consider it to be unperturbed, right? Unperturbed মানে it's just the scalar field, the underlying metric, and that's it, right? But of course we know that the universe does not work that way, right? You do not have any unperturbed or ideal situation where you can just compute the scalar field and the underlying metric and you're good to go. That does not work that way, right? We know in reality what we have is basically disturbances in the field, because any physical process is bound to make disturbances in the field. That is what we know. So indeed what we're going to work with, if we want to actually predict real stuff, meaning real stuff as in structure formation, the formation of galaxies, the formation of the CMB, the cosmic microwave background, and all of that stuff, you need to consider these disturbances. Because একটা undisturbed metric by the undisturbed scalar field doesn't give rise to anything. Okay, it's just free. So je kono kichu free thakle oটা will not really do anything. You need to disturb it to actually create something. Okay, so that is why we tend to focus on cosmological perturbations. which means that what you're doing is you're disturbing not only the underlying metric, which defines the underlying space-time, but also the inflaton field, which is dominating the inflationary epoch. Okay, so you consider perturbations to the metric and the inflaton field. Okay. Now, the way we do that is we consider the generic FLRW, and we perturb it by introducing some extra terms to the metric. Okay, so if you are not familiar with perturbations, well, it's just, like I said, disturbing the field. So if you have, let's say, some metric G mu nu, you can perturb this metric by adding an extra term. Okay, so what it does is it does not have the free metric anymore, but the total metric is now described by the metric and some disturbances around the metric. Okay. Now remember that these indices are important, because if you want to perturb something that has two indices, you need to perturb it with something that also has two indices. Okay. So let's say you want to perturb something that has no indices. Let's say something that is a scalar. You need to perturb it with a scalar quantity. So similarly for vectors, that will be true as well, right? So তার মানে আমি যদি এরকম একটা metric নেই যেখানে সব components আমার আছে, I have a scalar, I have a vector, I have a tensor, and so on, then I need to make sure that my perturbations are also scalar, vector, and tensor. Okay, so that is where the scalar, vector, tensor decomposition comes into play. And I write the metric as follows, which again remember is the generic FLRW, and I'm just perturbing it. And this is given as follows. Okay. Now this gamma ij is just the metric, let me write it as the spatial metric, because as you can see it has Latin indices INJ, and I am just perturbing the spatial metric with Hij, like I said. So now I have perturbations that are scalar without any indices, vector.
So this contribution, the perturbation that you are considering, is a linear perturbation or higher order perturbation?
আমি আপাতত হচ্ছে linear consider করতেছি, because all of these terms are linear that I'm adding. Okay, and in fact we will see that linear perturbations are what fuels primordial black hole formation. Of course I can add more, but the problem with that is it's very difficult to work with higher order terms when we are dealing with perturbation theory in general. আর আরেকটা জিনিস হচ্ছে যে perturbations are considered to be very small compared to the background metric, so therefore higher order terms eventually vanish anyway. They're so small that they're negligible. So linear perturbations use kora is more justified in this case. Okay, so this is the spatial metric, and Hij is just the perturbation that I'm adding to the spatial metric. Okay. Okay, and if we are considering that this FLRW is flat, which we normally do because we know the universe is flat, there is no surprise there, but in that case your gamma ij would just become delta ij. Okay. Now I will not waste time over here, but from here we can understand a couple of things. সেটা হচ্ছে যে the scalar part is important because it is the coefficient of d eta squared, where eta is the conformal time. Okay, and this tensor part is also important. However, this part is not important. Can anybody tell me why? Can you tell me why we don't really focus on the vector contribution? Anybody? People who have done cosmology maybe? The question is, why do we not consider the vector contribution to be important? Whatever, it depends on what I use. We are not considering, we actually break homogeneity and isotropy by introducing perturbations, right? Exactly. So because it contributes to mixed terms, right? And we know the metric is symmetric. So therefore, beta I eventually amneto, it vanishes away. So there is no point in focusing on something that would eventually vanish away. So what we do is we focus on the scalar part and the tensor part. Okay. Interestingly, the scalar part actually gives rise to structure formation, which is me, you, everyone over here, actually came from scalar perturbations that were left from inflation. Okay. The tensor part gives rise to gravitational waves, which is also something that has been recently, actually not very recent, when in 2015 was detected, which is also something very interesting that GR predicts. Okay. So these are the two things that we normally focus when we are dealing with a cosmological perturbation theory. But of course, for our case, where we are dealing with structure formation, particularly the formation of primordial black holes, we are going to only focus on the scalar part. Okay. So I'm just going to skip a lot of things over here, but like I said, these are in the note. If you ever are interested, you can go back and look. But one thing that I want to mention though, however, is the fact that GR is a gauge theory, right? Which means that it has gauge freedom and it has gauge redundancies, which requires us to fix the gauge, right? If you're not familiar with that, what that means is essentially you have extra degrees of freedom that are not physical. তার মানে হচ্ছে একটা থিওরির একটা সিমেট্রি এক্সিস্ট করতেছে, কিন্তু এটা আসলে ফিজিক্যালি তুমি অবজার্ভ করতে পারবে না। তো সেই ক্ষেত্রে অফকোর্স হোয়াট ডু আই ডু উইথ দ্যাট সিমেট্রি? দ্যাট সিমেট্রি ইজ ইউজলেস টু মি, right? What I want the theory to be is exactly physical. I want it to predict what is there, right? So therefore what I do is I get rid of the redundancies, I get rid of the extra gauge freedom by fixing a gauge, fixing one certain degree of freedom that I want to focus on, which is physical and which is what gives me the actual equations of motion. Okay. So therefore I will fix the gauge for this perturbed metric that I wrote over here. And the way I fix the gauge is by considering a couple of things, which is called the Bardeen potentials. I'm really breezing over a lot of things, but I don't have time. So the Bardeen potentials are actually denoted as phi and psi, and particularly phi is a combination of A, B, and the derivatives. So you see A and B come from here, and psi is a combination of particularly gravitational perturbations, which are the tensor part, like I said, and also depend on the scale factor. Okay, so তার মানে হচ্ছে এই phi যে Bardeen potential আমি বলতেছি phi, that takes care of the scalar part, the vector part, and also some of the tensor part, because I have a derivative term over here. Particularly psi takes care of the gravitational perturbations and the scale factor. Okay, so of course this is more in depth, but I'm just breezing over it to state that একটা particular gauge choice আমরা নেই যেখানে we consider that phi is equal to psi and E equals to B equals to 0. Okay, this is a gauge choice. মানে আমি হচ্ছে এই particular conditionটা imply করব, and এই particular conditionটা imply করে I will get rid of the redundant gauge freedom. Okay, and this is called the Newtonian gauge. আচ্ছা, ইটা হচ্ছে actually it comes from, আমি লিখি, I did not really do this, but basically it comes from the killing vectors. So if you make as such, like a change of coordinates or coordinate transformation as such, you will give rise to the killing vectors, right? Because you perturb the metric, you get something like this, right? And this will give rise to a particular term which is E equals to some E minus this particular killing vector. Okay. Now I did not really show you the details over here because that's not important for us to know. What we need to know over here is just the gauge choice, that I have this particular scalar quantity that you can add from dissecting or decomposing the scalar part over here, and they will give rise to this particular gauge choice over here. Okay, that is what's important for us to know. Okay, so now we have a particular gauge choice. এখন আমাদের next কাজ হচ্ছে আমাদের এটাকে incorporate করতে হবে in the gravitational part, in the sense that I need to put it in the metric, right? I need to put this gauge choice in the metric so that আমার একটা gauge invariant একটা theory আসে. Gauge invariant বলতে হচ্ছে আমার এই redundant gauge freedom গুলো আর থাকবে না. Okay. So now that is what I do exactly, and then I put it in my metric, and of course what do I do with the metric next? I compute the Kristeva symbols, right? And then with the Kristeva symbols I compute the Ricci tensors, and the Ricci tensors will be used to compute the Einstein's equation, right? And the Einstein's equation is the most important part because eventually that is what is going to give me the equation of motion, right? So therefore I will use this gauge choice to compute the perturbed Einstein equations, which will definitely be in a gauge invariant form. So let me just write the Einstein's equation directly because a lot of calculations over here, but again obviously it's here, you can go look at it if you want. So the perturbed Einstein's equation will look like the following, where I'm writing GI for gauge invariant. Okay, and once you solve this equation, what you will get is the following. Where there are many perhaps new variables over here that you are not familiar with, but these are the Burdeen potentials. And curly h over here is just a prime by a, where prime denotes a derivative with respect to the conformal time. Okay, so a prime is essentially dA by d eta. A is the scale factor, yes, and h is actually called the Hubble parameter, right? Okay, so this is something that is, I think, known to everyone, and I think you've all seen this before as well. Okay, so this is actually the perturbed Einstein equation now, which is gauge invariant. So তার মানে আমি আমার gauge redundancies গুলো I got rid of them. I have a equation that I now need to solve, which you can see is a second order differential equation, which I need to solve to get my equations of motion, right? In fact, this is the equation of motion, but এটা আমরা solve করে আমরা হচ্ছে actually phi মানে variableটা বের করতে পারবো by solving this equation of motion. So now what we have over here is this equation of motion, or basically the Einstein's equation, introduced two key quantities. Ekta hocche the Burdeen potentials, right, denoted by phi over here, and the gauge invariant inflaton potential, which is this one. This is the inflaton, if you remember. I started with the scalar field. Yes. Obviously, which we will see now in a bit. Okay, যে আমাদের এই ইকুয়েশনে আমাদের কি আছে, কয়েকটা জিনিস আছে, পার্টিকুলারলি দুটা। একটা হচ্ছে বার্ডিন পোটেনশিয়াল গুলো, যেহেতু আমরা গেজ চয়েস নিছি যে phi equals to psi, so তার মানে I can just denote this with phi overall, মানে big phi, capital letter phi, and I have small letter phi which is the inflaton, right? So এই inflatonের একটা ডেরিভেটিভ আমি নিছি এখানে, আর হচ্ছে বার্ডিন পোটেনশিয়ালস গুলো নিছি। সো এই দুইটা জিনিস কিন্তু নাম্বার ওয়ান গেজ অ্যান্ড ইনভ্যারিয়েন্ট, নাম্বার 2 হচ্ছে it describes both gravitational and matter sectors, right? কারণ স্কেলার ফিল্ড কিন্তু যে ম্যাটার পার্টার, লাইক আই সেড, যে আমরা এস ফাই লিখছিলাম না, দ্যাট ওয়াজ দ্য ম্যাটার অ্যাকশন, রাইট? সো ফাই অ্যাকচুয়ালি রিলেটস ম্যাটার, and the big phi, that means the burden potential, was a metric perturbation, if you remember, right? So the metric perturbations will take care of the gravitational sector. So now you have two things that are very important for us to actually determine the overall space-time: what the space is and what the space contains, right? Okay, so that is why what we do is we define a Mukhanov-Sasaki variable. This is named after two people, Mukhanov and Sasaki, which we write as a combination of these two things. That is the perturbed inflaton field, right, phi, which is again gauge invariant, plus the burden potential. Okay, and this variable is what is important to us, because আমরা এই ভ্যারিয়েবলটাকে, যেহেতু it is a combination of the inflaton and also the burden potential, which again gives rise to matter and gravitational sectors, we will use this particularly to figure out an equation of motion. Okay, তাহলে যেটা হবে যে equation of motion in hand we have, that will actually tell you how matter and gravitational contribution is affecting the overall equation of motion. Okay, does that make sense to everyone? Okay, second, we do the same thing. We take the action, we compute it by the Lagrangian, we vary the action, equate it to 0, and then solve, right? So eventually what I get is called the Mukhanov-Sasaki equation, determined by the Mukhanov variable. So let me denote k over here, and why I will tell that in a bit, which is given as follows. Where essentially this epsilon is called one of the slow roll parameters, which we introduced via the definition of the Hubble parameter. So slow roll parameters are essentially, okay, for people who have done cosmology, this would be something that you know already, but the slow roll parameter is essentially that something that maps the expansion during inflation. Okay, so this is something that tells you how much inflation is happening and when it will stop. Okay, so you use that, and of course that is also a function of the Hubble parameter. So you use that to define your Mukhanov-Sasaki equation. So this is what you have. So what you see over here is something that looks familiar in its form, at least, right? You have a second order differential equation, right? And then you have some coefficient with the Mukhanov variable, which is without any derivative equals to 0. What does this look like? Can you tell me? It looks like a wave equation, right? Right? It's a second order differential equation that looks like a wave equation. Like actually any second order differential equation in this form would give you a wave equation, a plane wave solution. So what's important from here, and what's interesting in fact, is now you have an equation of motion determined by the perturbations, burden potential, and particularly the perturbation of the inflaton field, that gives rise to a wave equation. তার মানে whatever perturbation that is seeded from here will act like a wave. Okay, and in fact that is what seeds the formation of primordial black holes. Now to understand that further, I'm going to draw a plot. So this plot is with regards to the co-moving scale, which is given as k inverse. K hoche basically, you can think of them as momentum modes, okay, or you can think of them as momentum modes. So basically, or physically, intuitively speaking, they sort of tell you the energy scale. Okay, So that means that if I have this on the y-axis, that means I'm sort of determining the plot over energy scales via the co-moving scale, and on this part I will have the scale factor. Okay. So this is a very famous plot. I don't know if you've seen this before, but what I'm trying to do is I'm trying to map the whole history of the universe in this plot, okay, in regards to the energy scale and the time, because the scale factor, as you can see, is also a function of the conformal time. Okay. So what it looks like is the following. Okay. Now, step by step, this part over here, we consider this to be when eta equals to 0. Okay. This part over here, which exists at negative eta, is the inflationary time. So this is when inflation took place. Okay. And all of these parts is after inflation. So this is the radiation dominated universe, this is the matter dominated universe, and this is where we are today. Okay, so this is now, which is also called the cosmological constant dominated universe. Okay, so this is where inflation took place. So our jono kintu A part ta important because we're looking at inflation particularly, right? And you can see it starts out at very high energy scales. No, sorry, it starts out at very high K inverse scales but very low energy scales. So if K maps energy, like just think about this, then K inverse would be inverse of energy, right? And therefore if I have high K, that would mean low energy. Okay. So in this case, this starts out with low energy, but eventually when we reach the end of the universe, it goes down to very high energy scales. Okay, number one. That means that the energy that is over here is what postulated the Big Bang, what we think about in the sense of early universe cosmology, right? But in fact, Big Bang didn't really exist. Like the explosion that we think about did not really exist. It was just a transition from inflation to radiation dominated universe. Okay, so this is where we think the beginning of the universe took place. Okay, inflation ended, then we have the universe that we see today. So আমাদের জন্য ইম্পর্টেন্ট হচ্ছে এই পার্টটা, বিকজ এখানে হচ্ছে এই পার্টারবেশনস গুলো সিড করতেছে, এই পার্টারবেশন গুলো হচ্ছে. So what happens during inflation is that you have the universe, because the universe is expanding, the particle horizon, or in this particular language we call this to be the co-moving horizon, it shrinks. Okay, and you can actually show that in many ways, but for now you have to take me as granted. If you have an accelerated space-time, you will see that the particle horizon actually shrinks. And if the particle horizon shrinks, that means whatever was inside the particle horizon would have left the horizon at some point. Right? Does that make sense to everyone? So let's say if I have a universe as such. Again, the universe is not a bubble, it's not a circle or whatever, but I just draw this for convenience. But let's say I have something that exists over here, some perturbation field. And I'm drawing it like this because, like I said, I got a wave equation, so might as well draw it like a wave, right? So if the particle horizon shrinks, eventually this would get outside the particle horizon, right? So eventually, if my horizon is smaller now, this would exist outside, right? So eventually what happens is these perturbations are seeded in inflation, but during inflation, as the particle horizon shrinks, they exit the horizon. Okay, and once they exit the horizon, they're stuck. And you see from here that এখানে কিন্তু আস্তে আস্তে ইনফ্লেশনের সময় your horizon actually shrinks, right? So this is also the horizon, which we denote as AH inverse. And when it shrinks, you have perturbations that, let's say, is seated over here, get outside the horizon. Okay, so when they get outside the horizon, now they're outside the horizon, they're outside, okay, fine. But eventually, they will come back. Why is that? Because once inflation ends, you don't have accelerated expansion anymore. So the space-time that was once shrinking, let's not call it space-time, but the particle horizon that was once shrinking starts expanding again. And we know we live in a sort of expanding universe, right? So যেটা আগে shrink হইতো, inflation শেষ হওয়ার সাথে সাথে ওটা আবার expand করা শুরু করছে. So of course যেটা হচ্ছে বের হয়ে গেছে, যে পার্টারবেশন গুলো বের হয়ে গেছে, সেগুলো আবার will come back inside or re-enter the horizon once the particle horizon starts expanding again, right? So which we can see from this diagram as well. Let's say there is some perturbation that was seated over here, it got out, and eventually it would come back in. Okay, so it is postulated that this is exactly when you have overdense regions which are seeded from these perturbations that gravitationally collapse and form primordial black holes. Okay, so primordial black holes, like I said, are given from these Mukhanov-Sasaki equation dominated perturbation fields. Okay. Okay, so this is how you can sort of formulate যে এই perturbation field গুলো যখন, of course depending on the type of energy that they have, you see this is a wave equation, so wave equation you can find out like someone was saying the energy required and so on, right? And depending on the energy scale, depending on how they are dynamic in their equation, they will give rise to overdense regions and gravitationally collapse. Okay, so once these perturbations gravitationally collapse, they will form compact objects which we now think as black holes. Now this is how primordial black holes are formed through causal processes. Now of course there is a threshold, right? Of course, I cannot just say that এরকম perturbation field গুলো বের হয়ে ঢুকছে and then they just formed primordial black holes. That does not really happen, right? So they have to abide by some conditions. So there is a threshold for collapse. আদৌ ইনডিড সব পার্টারবেশন ফিল্ডগুলো কি কোল্যাপস করে ব্ল্যাক হোল ফর্ম করবে কিনা বা সবগুলো উইল বা ইউ ক্যান অ্যাকচুয়ালি টেল যে হাউ বিগ দ্য ব্ল্যাক হোল উইল বি ওয়েন ইট গ্র্যাভিটেশনালি কোল্যাপস অ্যান্ড সো অন. সো দ্য থ্রেশহোল্ড for collapse is indeed there, and the way it works is that we consider that if indeed we have a particular dense region, then the overdensity of the perturbation, if it exceeds the square of sound speed, which is given as cs squared for this particular wave equation, for this one, then it will collapse to form primordial black holes. Now এখানে আরো অনেক কিছু ক্যাভিয়াটস আমি অ্যাড করতে চাই. সেটা হচ্ছে যে there is something also called the Thorne's hoop conjecture, which means that for indeed black holes to form, you need these, okay, so these are waves, right? So waves have wavelengths, right? And সেই wavelength এর গুলো একটা measurement আছে, so they are dimensionalized by distance, right? So there is a measure of what that distance is. So there is a hoop conjecture by Kip Thorne which says that this particular wavelength has to surpass the circumference of a particular region of the densely populated area. Okay, so this means, as let's say I have a densely populated region as such. Yes, densely populated বলতে হচ্ছে যে ধরো এখানে পার্টারবেশন গুলোতে এন্টার করবে, right? But there will not be one wave, there will be many. Wave density bolbo na, but let's say so let's say in this particular point in time, and let's say eta equals to eta I or something, a particular point in time there could be many perturbation fields that re-enter the horizon, right? So let's say অনেকগুলো একসাথে যদি re-enter করে, it's like all of a sudden they are active and they are together in one very densely populated area, right? So what will happen is they will start interacting gravitationally. And if they start interacting gravitationally, they are bound to gravitationally collapse if they abide by some conditions, right?
What exactly causing this overdense?
Oh, মানে two things. একটা হচ্ছে first you have a lot of perturbations that are seeded from inflation, and another thing is the universe is very small, right? So if the universe is very small and if there are many objects in the universe, they are bound to create overdense regions, right? So এই কারণে হচ্ছে আমরা একটা রকম একটা যে ওভারডেন্স রিজনের সার্কামফারেন্স চিন্তা করি, but this is a conjecture, we don't know if it's true. If the wave has a wavelength that is comparable to this particular circumference, then the perturbation will gravitationally collapse. So that is the Thorne's hoop conjecture. But this has been discarded because what this is based on is Newtonian gravity, and we know that Newtonian gravity in itself is flawed, right, to some extent. However, GR now comes in and predicts that you can still figure out a threshold for collapse for these primordial black holes, and this threshold of collapse has actually been calculated and is given as follows: delta C. This is an observational limit which you can figure out by looking at the anisotropies of the CMB. So it predicts that this is a threshold, delta C. Don't ask me what delta C is. This is an experimental factor which I actually don't know myself how this is computed. But it predicts that you have to have a threshold, delta C, which is roughly 0.4 for gravitational collapse to take place. And if delta C is roughly 0.4 or above, that means that region is dense enough for it to form primordial black holes. Okay. So now the question is, why do we study primordial black holes? Like, মানে অবভিয়াস তাই না, মানে ফিজিক্সের এরকম একটা জিনিস আমি কেন স্টাডি করবো যেটা হচ্ছে কোনো মানে এখন কোনো মানে ভিজিবল ডিটেকশন নাই, বা উই ডোন্ট সি ইট ইন দ্য নাইট স্কাই টুডে, রাইট? অ্যাকচুয়ালি উই ডু সি ইট বিকজ if you remember, like I said, primordial black holes were formed in a time where we did not have ordinary matter, right? They were formed from non-baryonic matter, and non-baryonic matter mane hocche they do not interact with matter in the same way that matter interact. Right? So tar mane ki? Tar mane hocche the only interaction that we can predict for primordial black holes is gravitational. Do you know something else that only gravitationally interacts? Dark matter, right? So therefore, primordial black holes are a natural candidate for dark matter. And in fact, if you can understand how primordial black holes are formed and study them, then you can potentially think about all the dark matter that we have existing in the universe today, which is abundant. Right? It is more than ordinary matter. Number one. Number two, হচ্ছে যে primordial black holes can be ancestors of the supermassive black holes that we see today in the middle of every galaxy. Okay, একটা প্রত্যেকটা supermassive black hole আছে না at the center of each galaxy. So সেই supermassive black hole এর ancestor আমরা হিসাবে চিন্তা করি primordial black holes, because of course primordial black holes are বাপ দাদার আমলের black holes, right? So what happened is, if you have a bunch of primordial black holes, they will obviously gravitationally interact and they will merge. And they have a long time to keep merging and merging and merging and merging, right? So what they do is they merge and they bring out these supermassive black holes that govern the center of galaxies, which eventually determines the structure of the universe, right? Because how the galaxies are laid out in the web, in the cosmic web, is how the cosmic web is going to be structured, right? Number two. Number three হচ্ছে যে এই primordial black hole formation থেকে কিন্তু আমরা অনেক gravitational waves পাইছি. So let's say if primordial black holes merge, they will cause ripple in space-time, and this ripple in space-time will be detected by LIGO and Virgo and so on. So you can have gravitational waves from them and we can detect them. So তার মানে if you can study primordial black holes and their mergers and connect how the physical mechanism gives rise to gravitational waves, you can have a connection to study dark matter, to study the early universe cosmology, and so on. So primordial black holes is an uprising field of research. Okay. Also, primordial black holes is a good way to look into when you're studying quantum gravity. Because when these, and this is also something that I'm working on particularly, is that when they were formed in the very early universe, they were very small. রাইট, কারণ যে আমরা চিন্তা করলাম না যে যদি ইউনিভার্সটাই ছোট হয় তাহলে প্রিমোডিয়াল ব্ল্যাক হোলস যখন ফর্ম হয়েছে তারাও ডেফিনেটলি ছোট হইতো, রাইট? আমরা নর্মালি অ্যাস্ট্রোফিজিক্যাল ব্ল্যাক হোলসের ব্যাপারে যেভাবে চিন্তা করি, দে আর অলওয়েজ গিভেন আ সেমি ক্লাসিক্যাল নোশন যে you have a classical object but you have quantum perturbations around the event horizon. But if primordial black holes are small in themselves, they require a fully quantum framework to describe them. So that means if you can formulate primordial black holes, you have to formulate a quantum framework for them. And if you have a quantum framework to determine something that is purely gravitational, you need a quantum gravity theory. right? So that is one of the approaches that we take to study quantum gravity as well. So the primordial black holes study is important because one, it gives you an insight into the early universe. How did inflation seed structure formation? How did inflation seed gravitational waves and so on? It tells you, or at least gives you an approach to quantum gravity, and also tells you how the universe is structured that we see today. Okay, so if you're interested in primordial black holes, you can come talk to me sometimes, maybe. So yeah, so this is what I wanted to talk about today, which I know is really over the top because I skipped a lot of things, but I wanted to give you a pedagogical idea of what primordial black holes are, how they form, and what you can do with it. So thank you all. Are there any questions?